Okay, hello. Thank you for watching this presentation. It's a real honor to have won the best poster at the 2023 AIVC conference, and I'm going to give a presentation on a study that some colleagues of mine and I did on the energy implications of increased ventilation in commercial buildings to mitigate airborne pathogen transmission. What inspired this study was, as everyone knows, with the recent COVID pandemic, there were a lot of recommendations to increase ventilation in buildings as a way to reduce COVID spread. But one thing that we thought of, and I'm sure a lot of you as well thought of, is that, well, all of this air in these commercial buildings or even residential buildings all needs to be conditioned, and conditioning air requires energy. Has anyone really thought about the energy implications of increasing ventilation to mitigate airborne pathogen spread? And we didn't really see much in the literature on that topic. So we thought we would do a conceptual study on two different building types, a low-rise building and a high-rise building in two different climates in America: New York City, where I live, which is a mixed climate, but what some people, there's a heating season and a cooling season, and Miami, Florida, which is very much a cooling climate. They don't have much of a heating season. It's primarily air conditioning year-round. And we looked at both implications of increasing filtration and increasing ventilation. So the first thing I will talk about is filtration. We found that with increasing the filtration ability of the filters within the air conditioning system or the mechanical system, that there is a slight increase in the energy use to power the fans, but there really wasn't a significant increase in the overall building energy use. And then we looked at increasing the ventilation, and we looked at increasing the International Energy Code, which is the code that most jurisdictions in America use. Looked at the baseline case, and then we looked at increasing ventilation 10%, 50%, or 100%, which we thought would be more practical for an existing building to try to do as a way to mitigate airborne pathogen transmission or COVID transmission. And then we looked at what the CDC recommends, the United States Center for Disease Control, which is 5 air changes per hour, which we interpreted to mean 5 air changes with fresh air. And we found that increasing incrementally 10%, even up to 100% over the International Energy Code baseline does increase the heating and cooling costs and energy use, a decent amount, but in terms of the overall building energy use, it doesn't have a significant impact. So this is probably a reasonable thing to do strictly in terms of energy use for a building. But if we try to go to 5 air changes per hour with outdoor air, we see that it's really completely impractical. Aside from the fact that the equipment probably couldn't even do it, the energy use and really increases very significantly for heating and cooling, and then the overall building energy use really increases. So understanding the implications of climate change and how much energy our buildings use in general in terms of the overall energy use of our municipalities and countries and so forth, this really is probably not a practical solution, and it has serious implications on carbon emissions and climate change and so forth. So that, while we understand the intent, that is something that really does probably need to be considered a little bit more closely. And another thing I want to address is the importance of balancing the mechanical system, because a lot of times in commercial buildings, office buildings or school buildings, the offices or the conference rooms or the school rooms are conditioned with forced air. But the corridors, the kind of more common spaces in between these individual rooms, often don't have their own supply and return, and they really rely on air transfer and bleed out from the adjacent spaces. So if your spaces if your mechanical system in your individual rooms is really well balanced, at least in theory, hopefully whatever airborne pathogens there may be are really contained within that room and drawn back into the mechanical system. But if the system is not well balanced, what can happen is that the pathogens are actually pushed out into the common spaces. So while increasing ventilation may have had the intent of reducing pathogen spread, if it's not considered carefully for an existing building, it can actually potentially lead to increasing airborne pathogen spread. So we really have to be very cautious when thinking about increasing ventilation as this kind of global solution to mitigating airborne pathogen spread, especially if anyone is considering utilizing this as a long-term strategy or as a general strategy just for building health in total, and not as a temporary solution for particular health events. So that's the end of our presentation, my presentation, I should say. So thank you very, very much. My colleague, Sean O'Brien, was the lead author on this paper, and I'm David Artigas. So if you have any questions, here's our contact information. We would love to hear from you. We'd love to discuss this more. And thank you very much.